In this video, I will discuss some more common misconceptions in mathematics. This is the second of two videos we have on this topic, and I encourage you to watch the first video if you have not yet done so. The statements you see here are all incorrect, but they are statements that I have seen students make many times. I believe that it is important to understand the reasoning behind the rules because you are more likely to apply the rules correctly and in the correct situation. And so I will discuss the reasoning behind the rules as well as the correct answers to these statements. I will also discuss why the statements you see here are incorrect. I will begin by looking at some common fallacies regarding operations with exponents. As I talked about in slide 10 of the first video, you can use the distributive property to add the like terms here. You can also think of n as representing potatoes. Thus, this problem would be telling you to put 5 potatoes together with 2 potatoes, and so you would end up with 7 potatoes. Here's another similar example. As I said earlier, many people try to tell me that x plus x is equal to x squared. However, you should realize that x squared is equal to x times x, and not x plus x. We can simplify this example correctly using the distributive property as shown here. Most people realize that this example is equal to 0a plus 5b, but then many of them try to tell me that this simplifies to a plus 5b. You should realize that this is not correct because 0a is equal to 0 times a, or 0. You should also realize that if you try to answer a plus 5b to this problem, you are saying the same thing as 1a plus 5b, and of course that is not correct. Next, let's look at what it means to multiply x to the second times x to the third. X to the second equals x times x, and x to the third is equal to x times x times x. So, when you want to multiply x to the second times x to the third, you are multiplying 5 x's together. Therefore, our final answer to this example is x to the fifth. As another example, to multiply negative 5n to the third by 2n, you should realize that you need to multiply negative 5 times n times n times n by 2 times n. Since this is all multiplication, we can do this in any order we choose, and so we can note that negative 5 times 2 is negative 10, and that we are multiplying 4 n's together. Therefore, the final answer to this example is negative 10n to the fourth. And here is another example for you to study. Now, let's look at another rule we use to simplify expressions involving exponents. If we want to raise x to the third to the fourth power, this means that we want to multiply x to the third by itself 4 times. We can then use the concept that we discussed in the last slide to say that this is equal to x to the 12th. This example should tell you why we must multiply the exponents in this problem. Note that you have 4 groups of 3 x's all multiplied together, and so then that would be 12 x's all multiplied together. As another example, to raise negative 2a to the fifth b to the seventh to the third power, we must multiply negative 2a to the fifth b to the seventh by itself 3 times. Then, after we have written this out, we can use the concept from the previous slide to say that our final answer to this example is negative 8a to the 15th b to the 21st. Here's another example for you to study. Our last rule for exponents that we will look at has to do with dividing expressions involving exponents. Note that x to the 8th tells you that you want to multiply 8 x's together, and x to the fourth tells you that you want to multiply 4x's together. Now, we can use a concept from the first video to simplify this. In slides 17, 18, and 19 of the first video, we talked about how we can reduce algebraic fractions. We can use that concept to say that we want to divide both the top and bottom by 4x's. Or, in other words, we can cancel 4x's from the top and the bottom. You should see that this leaves you with 4x's multiplied together on top. This should also help you see why the rule we use to simplify this problem says that we must subtract the exponents and keep the bases the same. Here's another example. Notice that we can divide both the 7 and the 42 by 7. Also notice that we can cancel 1x from the top and the bottom, and then we can cancel 3y's from the top and the bottom. This leaves us with just an x on the top and a 6y on the bottom. This example puts all of these rules together. I can raise 4ac to the fifth to the second power using the concepts I discussed in slide 27. Then I can simplify both the top and the bottom using the concepts I discussed in slide 26. And finally, I can simplify this expression further using the concepts I discussed in slide 24. Now let's look at some common misconceptions related to percents. We will begin by discussing two questions that seem to be similar but are actually very different. You should notice that these two questions are identical except for the words that come after the 20%. To find the answer to the first question, let's examine the first phrase of the second sentence. The word "this" refers to the 60 people. In general, verbs often translate to equals, and so the word represented means equals. Then, of course, 20% is equal to 20 hundredths. Next, we have the word "of," which means multiply when it comes after a fraction, decimal, percent. And finally, the number of people invited is what we are trying to find, so we will call that x. This gives us the equation 60 equals 20 hundredths times x, which we can solve by dividing both sides by 20 hundredths. This tells us that there were 300 people invited to this banquet. Now, as I said earlier, this question looks very similar to the last one. The only difference is the words "more than" after the 20%. To work this problem, we will use this formula. When we substitute the correct numbers into this formula, this is what we get. We can solve this equation by noting that x plus 0.20x is equal to 1.20x, and then dividing both sides by 1.20. This tells us that there were 50 people invited to this banquet. Now let's look at another example. Most people, when they read this problem, will say that the final answer to this question is $50. However, as you will see, this is not correct. We will begin by substituting our numbers into this formula. This tells us that the price is $55 after the price increase. Now, because we need to decrease the price by 10%, we need to change the formula slightly. Note that the addition changed to subtraction, and that we now talk about a percent decrease instead of increase. We can substitute the numbers into this formula as shown here. Note that the original amount is now $55. Also note that when you simplify this, you do not get the same $50 that we started with at the beginning of the problem, and the reason is because we changed the original amount. The final misconception I will talk about in this video concerns interest earned in a savings account and mortgage payments. Most students learn the formula interest equals principal times rate times time around the 7th or 8th grade. However, This is a formula for what we call simple interest. It will give you a good approximation of the amount of interest you will earn if you deposit a certain amount of money in the bank and leave it there for a while, but it is only an approximation. Let's look at an example that illustrates why this formula only gives you an approximation for the interest you will earn in a savings account. Suppose that you invest $4,800 in a savings account that has an annual percentage yield, or APY, of 1.5%. If we use the formula interest equals principal times rate times time, we see that you should earn $6 in interest each month. That comes from multiplying the principal of $4,800 times the rate, or 0.015, times the time, which is 1/12 of a year. However, if you earn $6 in interest after the first month, then that means you have $4,806 in the account to start the next month. If you use the formula interest equals principal times rate times time again, that means that you will earn $6.01 in interest the next month. Now, let's extend that out a few more months. The formula banks use to calculate the interest you've earned is actually more complicated than interest equals principal times rate times time, but we will use that formula for now. This slide shows you the amount of money you will earn each of the first 6 months while you leave the money in the bank. Recall that the formula interest equals principal times rate times time told us that we would earn $6 every month, and notice that that gives you a good approximation of the amounts that you will earn, but it is only an approximation. This slide shows you the formulas the banks actually use to calculate the amount of interest in a savings account. This thought process should help you see why we cannot use the formula interest equals principal times rate times time to calculate a payment for a mortgage or any other type of loan. When you make a payment on a loan, you pay off some principal and some interest. Let's look at an example. Suppose that I want to take out a loan for $135,000 at an annual interest rate, or APR, of 5% for 30 years. Using a formula that we will see in a minute, the monthly payment for this loan should be $724.71. Note that, as this slide shows, I will be paying off some interest and some principal with each payment. However, as long as I do not pay off the full balance, more interest will accumulate each month. This slide shows the formula that banks use to calculate a payment for a mortgage or any other type of loan. In my example, when I talked about getting a 30-year mortgage for $135,000 at an annual interest rate of 5%, the principal was $135,000, the R was 0.05 divided by 12, and the N was 360. If you have comments or questions about this video, please feel free to contact us using the Contact Us link on our website. Also, don't forget to watch the first video on this topic if you have not already done so.